This is my second video on Google Test and Mock platform. In this video, we focus on GMock matchers. We will cover topics such as expect that macro, string matchers, composite matchers, container matchers, custom matchers, and many more. What exactly are we covering? In the previous video, we covered Google Test and Google Test macros. If you're not familiar with those macros and Google Test in general, I invite you to watch that video first. Today, in this video, we will talk about Google Mock and matchers and expect that macro. In my third video, we will cover the rest of Google Mock, which is a tutorial on how to mock classes and functions using expect call and on-call macros. So let's get started and focus on Google Mock, matchers, and expect that. If you want to code along with me and run the examples that I show you yourself, you can clone this repo. The link is in the description. This repo can be run in Visual Studio Code using Bazel. The instructions on how to install and use Bazel is provided in the README file for this repo. You can also watch my video here that explains how this repo can be used. As far as running the examples in this repo is concerned, you don't need to be worried about details of Bazel. I've written all the necessary rules in this repo already, and you can use them as a black box. Please notice that Google Test can be used not only with Bazel, but also with other builders such as GMock. However, the focus of this video is on Google Test itself, not on how you build it. So if you want to use other builder platforms, I will leave that to you to read the documentation on how you can build it with GMock. All right, let's talk about what GMock matchers are and what is the usage of expect that macro. Remember from my previous video that in Google Test, in order to check the equivalence of two values, you use the expect equivalence, or you can use expect true to compare two variables together and make sure they are equal. Using Google Mock library, you can define something called a matcher, which is a template class. And once you define it, you can call its member function matches, which evaluates to either true or false. If the argument to this function is 1, then it evaluates to true, otherwise it evaluates to false. Similarly, if the argument of matches for is 0 evaluates to 0, then the whole thing evaluates to true, otherwise it evaluates to false. So this is yet another way to check if an actual value is equal or it matches the expected value. Google Mock provides one very powerful macro, which is called expect that. Expect that kind of works like expect EQ in the sense that it compares one value to another, but the other value can be a matcher. Let's see how that works. So I can rewrite this test in something that looks nicer using expect that and say 1 has to match is 1, 2 minus 2 has to match is 0, and 1 minus 1 has to match is true. So basically, instead of writing this, I ended up using expect that and writing something like this, which is not that interesting yet, but I guess you can accept that this is at least a little bit more readable. I will show you some more examples in a minute. Before that, let's review expect that. So expect that is a macro that you can compare a value, usually an actual value coming outside of a function that you want to test, and you want to compare to see if that value matches a matcher which is of this type. You can see these examples and run them yourself from this path in the repo that I provided. Here I'm showing our first example on matchers. It's called matchersintro.cc, and this file is inside the folder tests, GMock demo, and then matchers. Notice that now I will have to include both GMock and GTest because I'm using the matchers from GMock. Also notice that for all the constructs that I'm using from GMock and GTest, I will first have to declare them here so that I can use them without the namespace. Now, in order to run this, if you are inside the root directory of this repo, you can just type Bazel test and then the relative path of this file, which is matchers_intro without the .cc part. So I just type this and enter. Now Bazel is making this file. Remember that the rules for Bazel are inside this build file. For this video series, you don't have to be worried about the rules. I have written them all, so you can just use them. But if you want to change them, that's where to change. Now back to our examples, we can see that the test is passed and everything was fine. And as I have mentioned in my previous video, in order to see the output of this test, you can go under this folder called Bazel test logs, and then the same relative path to the file that we ran, which is tests, GMock demo, matchers, and then under matchers, we have matchers intro. Inside matchers intro, there's test log, and you can see the result. All other tests inside this video can be run in a similar manner, so I will leave that to you to try them. Let's look at a more interesting example. In this example, I'm not using the matchers yet. I'm using the plain expect true from Google Test or expect greater than and less than. So I define a string and I want to check if my string starts with hello. In order to test this, I have to write expect true and use the C++ rfind function to see if my string starts with hello. And also suppose I want to check if my string matches a regular expression. So in order to do that, I have to use std_regex match in combination with std_regex. So this is fine and we can do this, but notice that this is not that readable. And besides, what if I made a mistake in writing these functions or in using these functions? Normally, we want to avoid writing code and having calculations inside of our test code. Also look at this one where I want to check if one value is both greater than and less than two other values. So here I'm checking to see if 10 is both less than 0 and greater than 100. I have to do this in 2 lines by writing expect greater than and expect less than. Now let's implement the same test using GMock matchers. So this is the same string. I will have to include GMock now on top of GTest. And in order to test if a string starts with another string, I can take advantage of a matcher that GMock is already providing and just write if my string starts with hello. So compare this line with this line. This is more readable and also more reliable than the code that I wrote. And also, in order to find out if my string matches a regular string, I can use this other matcher called matches_regex, also from GMock library, and you just provide the regular expression. Again, notice that this is more readable and concise than what I wrote initially. Let's also look at this example where I'm testing 10. This value is at the same time greater than 0 and less than 100. I was able to do this in one single line and basically mention that I want test value to match all of the subsequent matchers which are greater than 0 and less than 100. Again, you can see and run this test from this path. So let's summarize why we use matchers. First, they are more concise and readable. As you saw in this line, I'm basically saying expect that my test string starts with hello. Everyone can quickly read this line and understand what it does. Yes, you could write these functions yourself, but the matchers are already tested and provided to you as convenience functions, so why reinventing the wheel? Next, as I showed you, they can be chained. So you can use matchers and combine them together to create more complicated matchers like this one. And last but not least, they can be customized. So basically you can write your own matchers. For example, here I'm defining a new matcher which checks if a value is divisible by n. So later on I can use it like testing here if 9 is divisible by 2 or not. Once you define your own matcher, then you can combine it with other matchers. For example, here I'm testing if 10 is not divisible by 2, or here I'm testing if each item in vector v is divisible by 2. So I hope you're now convinced that the matchers are very convenient to use, and a lot of them are provided to you which you don't have to test. And even if you insist on writing your own functions, you can expand on matchers and define your own. In the rest of this video, we'll go over the details of matchers and how you can customize them for yourself. Before that, let me just note that the difference that we saw for expect EQ and assert EQ in the previous video, in GMock, we have expect that and we have assert that. They both check the same thing. However, if you use assert that, the test stops right there and doesn't continue. But if you use expect that, if the expect that fails, the test still continues and the lines afterwards will still get executed. And one more thing that I want to mention is that all the matchers that we use here are in the namespace called testing from GMock, which you can either use by qualifying these names with testing or writing a statement like this using testing all of or using testing GT so that you can use them later without qualifying them with the namespace. First type of matchers that we talk about are comparison matchers. Comparison matchers, as their name suggests, are the matchers that are used for comparing two values. For example, here, if a is defined as being 1, then I can say expect that a is equal to 1. Or I could just simply write expect that a is 1. Some people find it more readable to use EQ because it's closer to reading an English sentence, and some people prefer not to use it. In this one, we are saying expect that a is greater than or equal 0. And similarly, this one is greater than, less than equal, and this one is not equal. So these are our very basic and simple matchers for comparison. You can run this example from this path here. For comparison of Boolean types, you can use is true or is false. Again, some people find this more readable to say expect that this variable is true or expect that this variable is false. There are some matchers for pointer comparison, is null or not null. So here I define 2 pointers and I can say pointer null is null and then expect that pointer valid is not null. Again, these are matchers that you could have probably lived without, but some people find adding them to your test make your test much more readable and closer to English language. Using a reference matcher, I can check if a variable is a reference to another variable. For example, here I have a variable called a, and I have a reference to a called aref. Now that I have this, I can say expect that aref is a reference of a. And similarly, for a separate variable called b, I can say expect that b is not a reference of a. And by the way, not is another simple matcher that you can chain with other matchers to invert their meaning. Type EQ matcher. This matcher is used when you want to check both the type and the value of a variable. For example, here I define a character called char a to have the value a, and I defined an integer called int a to also have the value of a. Now I can say expect that char a, its type is a character and its value is letter a. Similarly, I can say for char a, it's not true that its type is a character and its value is b, because although its type is a character, its value is a. Now for this variable int a, I can say expect that int a, its type is an integer and its value is letter a. However, if I try to say int a, its type is a character and its value is a, this would not be compiled. So this prevents me from writing a test and accidentally confuse the type of this variable. Wildcard matchers. A wildcard matcher is simply a matcher that matches anything. And Google Test uses underscore as its notation. So here I define two variables. One is of type integer, one is a string. And I could say expect that a is 1, or I can say expect that a can be anything. So underscore here matches any value that a can have. Similarly, underscore can match any other type such as a string. You will see more interesting examples of underscore when we introduce more complicated matchers in which you want to specify a variable matches anything, or basically you don't care about the value of a variable. So I will show you more examples of underscore later in this video. Now, if you want to do the same thing, but also check the type of the variable, you use a or an. So here I have two variables. One is integer, the other one is also integer. And here I'm saying expect that a is a variable of type integer. And similarly, here I'm saying expect that b is also an integer. Now, if I try to write expect that a is a character, this wouldn't compile, and this way I'm prevented from accidentally confusing the types of my variables. Again, you can run and play with these examples from the path here. Up next, the optional matcher. The optional matcher is useful when you have std optional in your code. Remember that std optional is a type to indicate your variable may or may not have a value. So here, opt has a value of 1, and no value is just a variable of type std optional, but it doesn't have any value yet. So defining these two, then I can say expect that opt is an optional variable with value of 1. And I would do this to emphasize that opt is an optional variable. I could have also simply written opt is 1. Now, obviously, I can also say this no value, which doesn't have a value yet, expect that no value is not an optional variable with value of 1. And if you want to make sure that it doesn't have any value, you can just say expect that no value matches std null opt. Basically, we are comparing no value with std null opt. Alternatively, std optional provides a method called has value. So you could have used this and say expect that opt has value is true, or expect that no value has value is false. Notice that I can chain optional with other matchers. So here I'm saying expect that opt is an optional variable which is less than 2. Up next, variant with matcher. This matcher is useful when you have std variant in your code. Remember that std variant is very similar to union in plain old C, where your variable can have either of the types that come in here. So this variable can be either an integer or a float. Now, if you're using the integer part, by assigning an integer to this variable, I can then say expect that this variable's value is 1, or if I want to highlight and emphasize that this is a variant, I can say expect that var is a variant with type integer and value 1. C++ STL provides std_get to get the value of a variant, so you could have used this, but this might be more readable, and also std_get can throw an exception. Here is another example in which we say expect that var is not a variant with type float and value 1, because obviously here we are using the integer part. Now, if you switch and use the float part of the var variable by assigning a float value to it, now I can say expect that var is a variant with type float and value 1.1f. As an alternative, I could have used std_get with float, or just simply say expect that var is 1.1f. Again, you would use this just to emphasize that this is a variant and also make sure that the type is not being confused. And finally, you can run all of these examples again from this path down here. So there you have it, guys. This is a summary of all the generic comparison matches that we talked about. I invite you to see the repo for examples of these matches and also review the Google test documentation for the details. Up next, string matches. For simple comparison of strings, you can either use str_eq or use str_case_eq. str_eq is just for highlighting or emphasizing that the matcher is of type string. So here I'm saying expect that str1 is a string and its value is str1. I could have also said str1 is equal to str1, or just say expect that str1 is str1. All of these work, this one just has the emphasis. So you have str_eq, you have str_not_equal, and similarly you have str_case_eq and also str_case_not_equal. These two should be used when you want to do a comparison where the case is not important. Again, you can run these examples from this path below. Here are more advanced and probably more interesting matches for strings. My favorite ones are the regular expression string matchers. There's two of them, contains regex or matches regex. As the name suggests, contains regex checks to see if your string contains a regular expression. And matches regex checks to see if your complete string matches a regular expression. The regular expression that you can use here are very flexible and they abide by POSIX extended regular expression syntax. So if you use a POSIX system such as Unix or Mac, there's a lot of features available to you. On Windows, the regular expressions that GMock provides are a little bit more limited. I suggest you refer to the documentation for details. Besides regular expressions, you have other functions. For example, you can check if a string starts with another string, ends with another string, or has another string as a substring. Again, you could have implemented these functions yourself, but notice how readable they are, and you don't basically need to worry about maintaining them or testing them. You can run this example from this path in the repo that I'm providing. Here is the complete list of string matchers. We have talked about most of them. There's a few more called isEmpty, which checks if a string is empty. There are two for checking equivalence or not equivalence of strings, ignoring the case, and there are two for checking the equivalence or not equivalence of two strings. Up next, floating point matchers. We have already seen macros from Google Test in my previous video. Suppose you have two floating point numbers which are very close to each other, and in particular, one is exactly one ULP away from the other. ULP in floating points is the smallest value that you can have between two consecutive floating point numbers. So this is usually very tiny, and we already saw that with the plain Google Test macros like expect not equal, we can verify that A and B are not equal. However, for some applications, because they are very close, you want to consider them equal. In order to do that, we already saw that you can use expect float equal and compare A and B with each other and basically declare that A and B are actually equal under expect float equal macro. So we have already seen these two macros in the previous video. In GMock, you can do the same thing using expect that and the macro float equal. So here I'm saying expect that A matches with float equal of B. Basically, we are saying A and B match with each other under float equal matcher. Similarly, we saw that in plain Google Test macros, you can use expect near and basically define what is the distance between A and B with which you still consider them equal or near. For example, here we're saying A and B are near to each other as long as their distance is no more than 0.2. And you can do the same thing in GMock by saying expect that A is float near B and 0.2. Basically, these two do very similar things. Another useful matchers in floating points are isNaN and NaN-sensitive float equal. Remember that NaN in floating point numbers just means it's not a number. And this happens, for example, when you try to calculate a value which is not defined. For example, if you want to find log of -1, the result would be a NaN instead of a valid floating point number, which we usually expect. C++ standard also provides some NaN types, for example, quiet NaN. The details for us today are not that important. Just know that you can use isNaN to test if a variable is NaN or not. For example, here I'm saying expect that QNaN is NaN and expect that logNaN is also NaN. Now, if both variables that you're comparing can be NaN, then you want to use NaN-sensitive float equal. So here, basically, I'm saying expect that QNaN matches logNaN under NaN-sensitive float equal. Notice that if I used float equal, these two wouldn't match, and that's why I use them not here. This is the summary of all the floating point matchers. We have talked about most of them. We have float equal and double equal for comparing double numbers, NaN-sensitive double equal and float equal for comparing two variables of type float or double, but also treating two NaNs as equal. And also we saw float near and double near to check if the distance of two numbers is less than this value. And equivalently, you have NaN-sensitive versions of these two. Now that we are done with the more boring matchers from GMock, let's get to more interesting matchers such as composite matchers. Composite matchers allow you to combine several simple matchers together and apply them all to a variable. For example, here, if A is equal to 1, I'm saying expect that A matches all of the following matchers. It's equal to 1, it's greater than 0, and it's less than 5. Next, I'm saying expect that A is not matching all of the following. In other words, A does not simultaneously match the following matchers: equal to 1, less than 0, and greater than 5. Notice that I changed greater than to less than, and 1 is not less than 0, so this one wouldn't match, and because this one wouldn't match, all of wouldn't match, and that's why when you invert it, it eventually matches A. Now you can say the same thing with any of. Here I'm saying expect that A matches any of the following matchers. It's equal to 1, or it's less than 0, or it's greater than 5. And because this one is true, the whole thing is true, and the expect that statement passes. Here is another example. So I have a string defined as follows. Now I can say expect that this string matches all of the following matchers. It simultaneously has substring AA and substring test, which you can see they exist here. And here I'm saying expect that str does not simultaneously match the following matchers. It doesn't simultaneously have AA and BB as str. Only AA appears here. However, I can change this to any of. The statement passes. So here I'm saying expect that str matches any of the following matchers. It has substr AA or has substr BB. And obviously this would be taken. There is a different version of any of and all of which accept its parameters in a vector or in an array. Notice that any of and all of here take the matchers as parameters. As an alternative, you can put all of your matchers inside a vector. So here I have one matcher and two matchers inside this vector called matchers. And then I can say expect that str matches all of the matchers inside this array or vector called matchers. So the same thing, rather than iterating all of its arguments in parentheses here, I put them inside a collection like this beforehand. Here is another composite matcher. It's called conditional. Using conditional, I'm saying expect that str, if selector is true, matches this matches, otherwise it matches this one. So conditional takes one parameter, which is the condition, and then resolves to the first parameter if the condition was true, otherwise it resolves to the second parameter if it was false. In essence, conditional is saving us from writing one if-else statement. It's a short way of writing an if-else statement, which some people find more readable. Again, you can check these tests and play with them from the file in this path. And here is the summary of all the composite matchers. We talked about all of array. All of array can take its parameters inside curly braces or inside a predefined container. This can be an STL-like container. Or you can provide the matchers using begin and end iterators. Or as an alternative, you can use plain C-style array. We also talked about any of. There's also any of array version of any of. You have already seen not. And we also talked about conditional, which resolves to the first matcher if condition is true. Otherwise, it resolves to the second one. All right, let's talk about GMock's container matchers. Again, this is where GMock matchers become interesting. So if you have watched the video this far, good for you. Let's get started. The first two matchers that I want to talk about are elements R and unordered elements R. These matchers are used if you want to compare the elements inside a collection. For example, suppose I have a vector whose values are these. Now later on, if I want to make sure these values are still in V, I can say expect that V, its elements are 3, 4, 5, and so forth. If you use elements R, you have to bring the elements in the same exact order that they exist inside V. However, if you don't want to bother with the order, you can use unordered elements R. So here we have a vector V whose elements are 3, 4, 5, and 2. Now here I'm saying expect that V, its elements are 4, 3, 5, and 2, ignoring the order. Or equivalently, you can say expect that there is a permutation of these numbers that match the elements of V. Up next, when sorted. So suppose I have my vector V defined like this, then I can say expect that V, when its elements are sorted, the elements are 2, 3, 4, 5, 6, and so forth. This is useful when you want to check the elements inside a container after sorting. There's an extension of this matcher called when sorted by, which takes one extra parameter to be used for sorting. So for example, if you want to sort in descending order, you can provide std greater and then say expect that V, when it's sorted by std greater, its elements are 10, 9, 8, 7, and so forth. Again, you can see this example and run it yourself from this path in the provided repo. There's a slightly different version of unordered elements R or elements R, which is called elements R array. So basically, instead of providing the elements as parameters of these matchers, you put them inside a vector or an array or a collection, and then provide that to the matcher. So here I'm putting them inside a pair of curly braces, and here I've put them inside a vector beforehand, and then I'm using iterators to specify the elements. This is very useful when you want to compare two vectors against each other. Or even it's useful when you want to compare two containers which are of different types. So this one is a vector, this one is a set. And here I'm saying the elements inside V matches the elements inside S when we ignore the order. Up next, each contains and subset matchers. Suppose you define your vectors like this. In the first statement, I'm saying expect that each item inside V is greater than 1. So notice that each will run the matcher on each element of V separately. If all were taken, then the whole expect that is satisfied. As you can see, this is very useful and it saves us from writing a for loop. In the next example, I'm saying expect that V contains the value 6. As you can see, 6 exists inside V. Up next, I'm saying expect that U is a subset of V, which means all the elements inside U should also exist inside V. Notice that you can also chain these matchers together. For example, here, I'm saying expect that V contains one element that is greater than 1. Or more accurately, we are saying expect that V contains at least one element that is greater than 1. Now let's look at this one. Here, we are saying expect that each element inside V matches any of these matchers. It's greater than 2 or it's less than 0. So in short, we are saying expect that each element inside V is greater than 2 or less than 0. You can see how powerful these matchers are, and you can use them and chain them to create very complicated matchers. There's another version of contains which works with duplicates. So for example, here I'm saying expect that V contains element 3 times. So element 3 appears 3 times inside V. And here we are saying expect that V contains 4 2 times. As you can see, 4 appear 2 times inside V. And here I'm saying expect that V contains 1 0 times, or in other words, 1 doesn't exist inside V. Another interesting matcher is called pointwise matcher. And this is used when you want to compare the elements inside two collections pointwise. Basically, I want to do a comparison between 1 and 4, and a comparison between 2 and 5, and a comparison between 3 and 6. So here I'm saying expect that the left-hand side vector is pointwise less than the right-hand side vector, which means every item in this vector is less than the corresponding item inside this vector. 1 is less than 4, 2 is less than 5, and 3 is less than 6. Again, you can chain this with other matchers. So here I'm saying expect that left-hand side is not pointwise greater than right-hand side. Obviously, the items inside left-hand side are not pointwise greater than the right-hand side. One more container matcher is called container equal, which is used for comparison of two containers. So here I have two non-equal containers, V1 and V2. And if you compare them using expect that V1 matches V2, the comparison will fail and the test will fail. And you will see something like this in the report. It says the value of V1 expected to be equal to 1, 2, and 3, which is V2, but its actual value was 1, 2, 3, 4, and 5. In other words, they don't match. So this is fine, but if you use container equal and compare V1 with container equal to V2, your report will be a little bit more readable and more complete, which mentions what items are missing. So basically, the reason that V1 doesn't match V2 is that items 4 and 5 are missing in V2, and this is something that the report mentions if you use the container equal matcher. So there you have it, guys. This is a summary of all the container matchers. We have talked about most of them. There's a few less important ones that I haven't talked about, and I invite you to read the documentation yourself and read the details. Up next, member matchers. Member matchers are used when you want to talk about members of a container or an object. Let's see an example in which we talk about pair, key, and fields are matchers. Suppose I have a map of integer to an integer whose values are these pairs. And remember, each element inside a map is of type std pair. Now, in the first statement, I'm saying expect that each item inside M is a pair whose first part is greater than 0 and the second part is greater than 99. So notice that for each pair, I can say the first part is greater than 0 and then the second part is greater than 99. In the next statement, I'm saying expect that the key of each item inside M is greater than 0. Usually, the first item in a pair inside a map is called a key, and then the second item is called a value. So key would match to the first item. So this way, we are basically projecting the map onto its keys or onto its pairs. Now, here's another example in which we use the wildcard. So here, I'm saying expect that each item inside M is a pair whose first value can be anything, and we don't care about it, but the second value should be greater than 99. This is a great example usage of a wildcard matcher that I promised to show you before. Another matcher which matches the fields of a container or an object is called fields are. So here I'm saying expect that each item inside M has the following fields. the first field matches greater than 0, and the second field matches any of greater than 100 or equal to 100. So in short, we are saying the first part of each pair is greater than 0, and the second part is greater than 100 or equal to 100. You can run this example yourself from this path. Up next, fields are for tuple and struct. So fields are can also be used on std tuple. Let's say I have a tuple which has int and std string. The value of my tuple is 7 for the int part and hello world for the string part. Now I can say the fields of my tuple, the first one is greater than 0, which is true because the first one is 7, and the second one has substr hello, which is also true because my string is hello world. So fields are is used to separate the fields of my tuple. You can also use fields are on a struct if you have C++17. Suppose I have a struct that has an integer value and a string. The integer value is 42, the string is aloha, and now I can say expect that S has the following fields. The first field is 42 and the second field is aloha. So this is how we separate the fields of a struct. Now if you want to do something similar on a class, you can use the field matcher. The field matcher takes two parameters. The first one is a reference to the field that you're interested in, and the second one is another matcher. So let's see an example of this. Suppose you have this class which has one field called m. Now suppose I define an object of this class and I set its field m to have value 1. Now I can say either of these two statements. Let's look at the second one first. Here I'm saying expect that my object m is greater than 0, which is true because I set m through the constructor to be value of 1. Instead of this, I could have said expect that the field m inside my object has value greater than or equal to 0. So these two are very similar, and you might ask, why should I use this more complicated one compared to this? And the answer is that the main usage comes when you want to chain this with other matchers. Let's look at this example. Suppose you have a vector of objects of this class. One has its field m to be 1, the other is 2, and the last one is 3. Now I can say expect that each item inside my object has its field m to be greater than or equal to 0. Or here I can say expect that the elements inside my object, ignoring the order, if you look at their m part, are 1, 3, and 2. So notice how we are projecting the object into its property using the field matcher. Very powerful, and you can see you can make very complicated matchers using the field matcher in combination with other matchers. Again, you can run this example yourself from this path. Now the next question is, what if m is private? How can I access it? So if you have a class like this and you make m private, and then suppose you define an accessor or a getter for this member variable. If that's the case, then you can use the property matcher, which takes two parameters. The first one is the name of the property, and the second one is a matcher. Let's look at an example. Suppose I define an object of type myClass2, and I set this private member to 1. Now I can either say expect that my object getM, which returns m, is greater than or equal to 0, or I can say expect that my object, its property m, has a value greater than or equal to 0. And again, the reason that you might adopt this more complicated version is when you want to combine it with other matchers. So let's look at this example. Here I have three objects whose m member variable is 1, 2, and 3. In the first statement, I'm saying that expect that each item inside my object, its property getM, is greater than or equal to 0. And here I'm saying expect that the items inside my object, ignoring the order and only looking at their getM property, are 1, 3, and 2. So you can use property matcher, as we saw here, with any member function inside the class, as long as it takes no parameters and it is declared as const. So it has to take no parameters and it should be declared as const. And finally, here is the summary of all the member matchers. We have talked about all of them. Again, I invite you to look at the documentation for more details. Pointer matchers. Before talking about pointer matchers, let's get the big picture. Remember that if you define a variable and then a pointer to that variable, for example, here I have a variable a, and then a pointer is pointing to a. Then I can say pointee of a pointer is a. That means what a pointer is pointing to. And then pointer of a pointer is a pointer itself. Basically, when I say pointer of something, I mean that thing contains a pointer. This will become more obvious when we talk about unique pointers. And then finally, address of a is inside a pointer. So these are the three things that you can define once you have a pointer and a pointee. Let's look at this for smart pointers, and in this case, a unique pointer. So if I define a unique pointer that is pointing to a variable with value 10, then I can say pointee of this unique pointer is 10, obviously, and then pointer of this unique pointer is a raw pointer that you can access to it with uniquePointer.get, which is what I'm doing here. And then finally, the address of this variable is inside the unique pointer. So these are the three simple definitions that you can have once you define a raw pointer or a smart pointer. And based on these matchers are defined. When you apply the address matcher on an argument, you get its address. Or in this case, you get the result of std address of that argument. And then the pointee matcher will give you what that pointer is pointing to. In other words, pointee has something to do with dereferencing our pointer. For example, the pointee of a PTR is A, which is when we dereference this pointer. We will see many examples of this in a minute. Now, you might still be confused about this matcher, pointer, which, as I mentioned, for a raw pointer is itself, and for a unique pointer is the raw pointer that is inside that unique pointer. Using the pointer matcher is not that common, and it doesn't have too many applications, but I will show you guys some examples of it nevertheless. There's one more matcher for dynamic cast, which I will talk about that in the end. So let's get started and talk about all of these matchers one by one. The first matcher that we want to talk about is called pointee. And as I mentioned, when you define a pointer that is pointing to a value, then that value becomes the pointee of this pointer, which is equivalent to dereferencing that pointer. So I can either say, expect that star end pointer is 10 or it's greater than 9, or I can say, expect that end pointer, its pointee, which is now the value of 10, is greater than or equal 9. So these two are equivalent. You can either dereference the pointer yourself, or you can use pointee to dereference that pointer. And again, you guessed it right. One of the reasons that we use this matcher instead of simply dereferencing the pointer is to use that in more complicated matchers like this. So suppose I have a vector of pointers. So in this case, I have two variables, and my pointers vector contains pointers to these variables. Now I can write something like this. I can say, expect that my pointers vector, each item in it, when dereferenced, is greater than or equal 0. And as you can see, this is the case for both A with value 1 and B with value 2. Or I can say, expect that the elements inside my pointers, ignoring the order, when dereferenced, are B and A. And notice that I wouldn't have been able to write it like this. Because this is a vector of pointers, I cannot check its elements using B and A directly. I had to run another matcher on its elements so that then I can match them with B and A. So in short, the pointee matcher, all it does is it dereferences the pointer. Now let's see the same thing with smart pointers. Here I'm defining a unique pointer that is pointing to a value of 10. Now I can either say, expect that star end pointer is greater than or equal 9, or I can say, expect that end pointer, its pointee is greater than or equal to 0. And just like before, I can create a vector of unique pointers. In this case, I have two unique pointers inside this vector called my pointers. The first one is pointing to a value of 1, and the second one is pointing to value 2. Now I can write a statement like this. I can say, expect that each item inside my pointers, when it is dereferenced, is greater than or equal to 0, which is the case for both 1 and 2. I can also say, expect that the elements inside my pointers vector, when they are dereferenced, are 2 and 1, ignoring the order. As always, you can run and play with this example yourself from this path down here. Now let's look at the address matcher. The address basically gives you the address of its parameters. So for example, here I have a variable called n with value 10, and I have two pointers pointing to that variable, n pointer 1 and n pointer 2. Now I can say, expect that address of n matches n pointer 1. Or I can say, expect that address of n matches both n pointer 1 and n pointer 2. Here is another example of using the address matcher with a container matcher. So here I'm defining a vector of two elements, 1 and 2, and we know the items inside a vector are in consecutive addresses. And because of this, I can say, expect that the elements inside my objects, when you look at their addresses, one is in the address of my object's vector, and the other is in the address of my object's vector plus 1. In other words, they are in consecutive addresses, which is what we expect from a vector. Here is one more matcher which might be a little bit confusing, and that is the pointer matcher. As I mentioned before, when you use the pointer matcher, what you are saying is that the argument has a pointer that matches what comes here. So here I have one variable and I have two pointers pointing to that variable. In the first statement, I'm saying expect that address of n is a pointer that matches itself, address of n. So nothing that interesting. Let's look at the second one. I'm saying expect that n pointer contains a pointer whose value is address of n. And finally here, I'm saying expect that address of n contains a pointer which matches all of the following. It contains a pointer whose value is n pointer 1, and it contains a pointer whose value is n pointer 2. As you can see, the pointer matcher doesn't do anything really that interesting when it comes to raw pointers, but it has some applications when it comes to smart pointers. So let's look at that. Suppose I define a unique pointer that points to a value of 10. Now I can say expect that n contains a pointer whose value is n.get. And similarly, if I define a second pointer, I can then say expect that a does not contain a pointer whose value is bget, although a and b both are pointing to a value of 1. Still nothing that interesting. Still probably you wouldn't use this. Let's see yet one more example. In this example, I'm defining a vector of unique pointers, and I'm pushing two unique pointers inside my vector. One is pointing to value 1 and one is pointing to value 2. Now let's say later on you want to check the elements of this vector. How would I do this? Could I just write my pointers and then unordered elements and then put two unique pointers here? We know that unique pointers cannot be copied, so how would I provide them to this unordered elements R without copying them? And that is not possible, or at least not simple to do. So one way around it is to use this pointer matcher and basically say expect that the elements inside my pointers vector contain a pointer whose value is my pointers 1.get and contains another pointer whose value is my pointers 0.get. Unlike the unique pointer, the raw pointers can be copied. In order to understand this, let's look at the same example with shared pointers. Let's say I define two shared pointers and then I put them inside a vector. And this is easy because shared pointers can be copied. Then I could easily say expect that my pointers, its unordered elements are a pointer and b pointer. And this is possible because a pointer and b pointer can be copied and then used by this matcher internally. If you try the same thing with unique pointers, because they are not copyable, you will get a compile error. So in short, one application of the pointer matcher is to work around this limitation for unique pointers. And this is the only practical application of the pointer matcher that I know. If you guys know anything else, please let me know. All right, let's talk about the last pointer matcher, which is when dynamic cast to. Remember, in C++, you can have polymorphism by defining a virtual function in a base class and then define a derived class which inherits from the base class. Having this definition, then you can define an object of type derived, and then you can define a pointer of type base that can point to that derived object. So this pointer, base pointer derived, is defined as a pointer that is pointing to the base class. However, it is pointing to an object of the derived class. Suppose I define this pointer and also I define a base pointer that is actually pointing to an object of type base. So this one is a base pointer pointing to base. This one is a base pointer pointing to derived. Also, remember in C++, dynamic cast can tell you at runtime if this pointer is pointing to the base object or to the derived object. So then I can say expect that if I take the base pointer derived, which is pointing to this object, and I dynamic cast it to the derived object, this should be valid and it should not be null. So I can say expect that the result of this statement is not null. I could take one step further and say if I dynamic cast this to a derived object, I can even take its field I, which is defined here, and I can check if its value is 4, which we set here. However, remember that if you take this base pointer and try to cast it to the derived object, you would get a null pointer. And that is what we are saying here. We are saying expect that if you take the base pointer and try to dynamic cast it to the derived object, the result would be null. So up to now, this is nothing new. This is just a reminder of how dynamic cast works in C++. So you can either use the plain C++ dynamic cast to write these checks, or you can use when dynamic cast to matcher. So here I'm saying exactly the same thing that I was saying here. We are saying expect that the base pointer derived, when it is dynamic cast to a derived object, would not be null, and it would in fact be a valid pointer. And the second statement is equivalent to this one. I'm saying expect that the base pointer derived, when it is dynamic cast to a derived object, its I field, which is defined here and is assigned here, would have a value of 4. So you can see the application of when dynamic cats do is basically the same thing that you would have written using plain dynamic cats from C++, but probably a bit more readable. And as you can guess, you can now use this in combination with other matchers and chain them if you want. Up next, matchers and predicates. Remember that a predicate is a function that takes some parameters and returns a Boolean result. In this case, we are checking if the parameter is positive or not. Remember from the previous video, if you have a predicate like this, then you can use either expect true or expect predicate with one parameter to check if something is positive or not. So here I'm saying expect true that 10 is positive, and here I'm also saying expect the result of this predicate with parameter 10 is true. So you could use these macros, which are from GTest. So this is fine. You can use these macros and there's nothing wrong with that. However, it's probably not ideal when you have a vector and you want to check this property on all of them. Then you have to write a loop and then write expect true or expect predicate inside the loop. And we don't generally like this. We don't generally like to see loops like this in a test. And that's when the GMock matcher truly helps. Instead of using these macros, you can use our familiar expect that macro and just say expect that 10 matches is positive with the truly matcher. So all I'm saying here is that expect that 10 is positive. So compare this statement to one of these statements. And the real power of this would become obvious when you have a loop. So you can write something like this. You can say expect that each element inside my v vector is positive. Compare this one-liner with this loop here. And that is basically what the truly matcher is doing. It basically allows you to take a predicate and combine it with other matchers. Again, you can run this example yourself from this path down here. Up next, custom matchers. Before I continue, let's get the big picture. In this section, we want to be able to create new matchers of our own. For example, is even or is between are the matchers that don't exist inside GMock, and in the next few slides, we will learn how to write them yourself. And there are two reasons that one would consider writing new matchers. One is to combine them with other matchers or chain them with other matchers, and the other would be to customize the output in the report. So let's see how that works, and let's see some examples. You can define a matcher using the matcher macro, the name of the matcher, and then a string that describes the error in the report, and then what the matcher is doing. So let's see a simple example here. So let's say I want to define a matcher that checks if its argument is even or not. So I would write matcher is even. Let's say I don't want to customize the output in the report, and then check if the remainder of the argument by 2 is equal to 0 or not. So this arg is a reserved name that is basically available to us inside the matcher body, and it results to the argument that is passed to is even. What am I saying? Let's look at an example. So if I define is even like this, then I can say expect that 9 is even. What would happen is that 9 would be passed to our matcher, and in other words, arg would have the value of 9. And similarly, I can chain this with not, and I can say expect that 10 is not even. Now, if you look at the report, obviously this check will fail, and you would see that the output in the report mentions that I expected 9 to be is even, but its actual value is 9. Where did this string come from in the report? If you look at this string, this is nothing but the name of your matcher itself. So what GMock does is that it takes this name, it understands the camel notation, and it puts a space between is and even, and it basically prints it right here. And if you use that matcher with not, it just puts a not, and then inside parentheses, it takes is even, it separates the two words, and it puts them right here with a space. In the next slide, we will learn how to customize this string. But before that, let's just quickly review what we learned. So we learned that you can write a new matcher using this statement, matcher, and then the name of the matcher, the customized string here, which you saw that because it's empty, the GMock framework took this string instead of this parameter from the name itself. And then we also learned that arg here is basically the argument that is passed to our matcher. So you can refer to it with arg, and you can refer to its type with arg type. As I mentioned, next you will learn how to customize these messages. So these messages can be customized using this parameter or using another reserved name called result listener. Let's see some examples. Here I'm defining a matcher that takes extra parameters. Basically, I want to say something like this. Expect that 100 is between 9 and 11. You can see that is between takes one parameter, which is 100, that is our matcher parameter. It takes two extra parameters, 9 and 11. In order to define something like this, you use matcher underscore p and then the number of the extra parameter. In this case, I have two parameters, so I would write matcher p2. The name is between comes as the first parameter here, and then the extra parameters are listed as a and b. And finally, let's customize the report message. So here, as the third parameter, I write a string that resolves to either is between 9 and 11 or it is not between 9 and 11. How do I do this? I use another reserved name, which is negation. If my matcher is used in combination with a not, this would have value true, otherwise its value would be false. This is something that the Google Test platform does for us. So for my customized message, I will say if negation was true, then use isn't, otherwise use is, and then between, convert A to a string, convert B to a string, and that's it. The body of the matcher checks if its argument, which is this value, is between A and B, which are these two values. Now let's look at the output. Here I'm checking if 100 is between 9 and 11, which it obviously is not. So I will get a message like this. I will see that expected is between 9 and 11. And this is exactly what we specified here. Negation for this case is false. So we take is, and then between, and then the value A, the word and then the value B. This is exactly what we wrote here. Now let's look at this example. Expect that 10 is not between 9 and 11. This obviously is not the case. 10 is actually between 9 and 11. So the output says expected isn't was printed because we have not here and negation evaluated to true. So here we are saying expected 10 isn't between 9 and 11, but the actual value was 10. So here we learn two things. First, we learn how to write a matcher that takes extra parameters, and also how to customize the output message as you saw here and here. The reserved names that are available to you inside the body, as I mentioned, are arg, type, and negation. There's one more, which is for further customizing the message, which is this part of the output in front of the actual. So this one, result listener, has something to do with what is being printed here. Let's see an example of this one as well. Let's look at this example. Here, we're writing a new matcher that checks if a number is divisible by another number. So I'm using matcher P, which takes only one extra parameter here. The name of the matcher is divisible, the main parameter, and then the extra parameter that is passed to my matcher is here. And this would be the output message. For now, I'm using the default, which would be is divisible by, that's generated by the Google Test platform. However, notice that inside, I'm using result listener, which prints something extra for the actual part. So let's look at this example first. Expect that 9 is divisible by 2. This obviously is not the case. So let's look at the output. First, it says, I expected 9 is divisible by 2. This was generated from is divisible by and this parameter. We did not customize this part. However, its actual value was 9. This part was customized by us, where the remainder is 1. This is what we sent on the result listener, where the remainder is arg, which is this value, %n. And this part is obviously the actual check. So let's look at this example. Expect that 10 is not divisible by 2. Again, the expected part we didn't customize. It's just not because we use not here. And then is divisible by 2 was generated from is divisible by 2, the name of your matcher, which Google Test took and put a space between each two words. However, we customized the actual part where the remainder is 0. That is what we calculated here, where the remainder is arg %n. So there you have it, guys. Now you know how to write custom matchers, which take extra parameters. And on top of that, you can customize both this part and this part in your output. You can run these examples yourself from this path. Finally, here are simple examples that show you how you can combine other matchers with your custom matchers. So here I have a vector and I can say, expect that each item in my vector is divisible by 2. Or I can say, expect that the elements inside my vector, the first one is less than 5, the second one is even, the third one is between 1 and 10, and the last one is not between 5 and 10. Notice that these are the matchers that I wrote and these are customized. And finally, here I'm saying expect that each item inside V is not between -1 and -2. Here is the summary of all the matchers that I showed you. You can either use the matcher macro to create a matcher that doesn't take extra parameters. The first parameter is the name of the matcher, and then the second parameter is a description that will show up in front of the expected part in the report. If you leave this empty, Google Test will create a string out of the name of your matcher, something like this. I also mentioned that arg is a reserved name that evaluates to the parameter that is passed to your matcher. Next, I mentioned that if you use a matcher that takes one extra parameter, you use matcher underscore p, and I showed you this example is divisible, which takes one extra parameter. If you need more extra parameters, then you use matcher underscore p2 or you use matcher underscore p3 and so forth. We saw that you can customize the actual part in the report using this reserved name called reserved listener, which is really a pointer. And also we saw how you can customize the expected part by not leaving this part empty and providing a string. This is what we are doing here. We use the negation reserved name to find out if the matcher is used in front of a not matcher or not. And we used print to string to convert the value of the extra parameters to a string. This concludes the second video on Google Test and Google Mock. We just covered this part, which was Google Matchers and the expect that macro. Please stay tuned for my third video on Google Test and Google Mock, in which I will go into details of using two other important macros called expect call and on call. Thank you for watching this video. Please support my channel by liking the video, sharing it with your friends, and also subscribing to my channel. Hopefully I will see you guys in the next video.